Okay, so just same announcements basically as last time. Homework D2 is posted. A couple of tips here when you're doing that homework. This is a homework that's meant to be part of exam practice. There will be at least a little bit of the exam that will go over random variate generation. Of course, as it is an online exam and it's auto-graded, I'm not gonna, have you be doing things that are going to need to be sort of manually graded, but might break down some of these random variant problems into little sections that you'll sort of do every section, and that's how we'll end up scoring you, so that way it's not like you're doing one big problem and then hopefully getting partial credit, but then if you screw up something up here, then by accident, then it messes up things down here. We're going to be broken up into kind of these multiple chunks. So you might on scrap paper, and by the way, you can have as much, or I think the online it might say 2 pages of scrap paper, but along with your formula sheets, if you think that'll be helpful to you. And so you might work something out on scrap paper, and then up to a particular point in the random variate generation, answer that, go to the next question, and it'll sort of have you pick up in the random variate generation and from another point. So you expect 2, maybe 3 questions about random variate generation, and this homework is supposed to sort of provide some practice of that. And one of the trickiest things about it, because you're like, why am I doing integrals again? The thing that find most people seem to, there's 2 things, and this is kind of, basically question 1 and then question 2 of this homework, is that remembering your limits of integration when you're integrating a piecewise function is something that was taught at one point, but it's not practiced a lot, and it's used a lot when we're doing this type of work. And so we just want to sort of make sure that everyone remembers how to deal with these limits. And so the key thing, and there's hints for this elsewhere, and right in the homework, I do an example for you. There's a video attached. So if you go to the homework page, I've got a bunch of resources there on how to do this, where I step through this for a different problem. But the key thing here is that when you're doing this integral, which you need to do to make a CDF, it goes from -infinity to x. If your f of, in this case, f of u, because I just use u as our dummy variable, are inside there, if that nuisance variable that's integrated out in the middle of that range from -infinity to the x you're going up to changes its form, you have to break that up into the integral into 2 integrals, an integral going up to the point where it changes, and then an integral from that point up to the x that you actually care about. So if you've got, f of x looks like 5 from -infinity to 6, and then it looks like 5x from 6 to wherever you're integrating to, 6 to 10, but you're integrating up to 8, for example, then you have to take the integral from -infinity to wherever I said 6 of that 5, and then that becomes a constant, and then add that to the integral on the other side of it. So as you integrate multiple pieces, you basically keep picking up constants from those pieces that you're totally integrating under on kind of the left-hand side. So that's what I'm saying here, and hopefully it'll become clearer as you do this, because I'm basically give you a density function that has, I think, 3 pieces. And so as you integrate through it, the first piece will be easy. It won't have any sort of baggage you have to carry through. But then once you go to the second piece, you'll need to take all of that first piece and add it to the second piece. The problem that people usually have is when they look at a piecewise function, like we'll see in lecture E2 next time, when they look at a piecewise function, they just want to integrate every piece independently. They say, oh, well, this piece is x. I integrate that to x squared over 2. This piece is 1. I'll integrate that to x. This piece is e to the x. I'll integrate that to e to the x. But that's not how you do it, because the second piece is sort of the integral of the second piece has to include all of the contribution from the first piece, because it's a cumulative distribution. So you're not just taking the antiderivative from one piece to the other, you're actually taking the integral, including all the previous pieces. And that's what I'm saying right here. And so that'll become, I think, clear when we do an example. And I think when you see the homework, it should hopefully become clear. But if you just find yourself doing an antiderivative, like, oh, this is easy, from like -infinity to 6. I'm going to take this antiderivative and I'll make it from -infinity to 6. And then for this next one, it's from 6 to 7. Well, then I'll just take the antiderivative and do 6 to 7 and so on. If you just find yourself copying that over and not carrying anything through, you're missing this piece right here, and you need to make sure you do that. So that's one hint. The second hint is in the second question. Because we have to do this inverse operation when we do these random variate generations, we have to remember all these tricks on when we invert functions. And remember that when you invert things that look like squares, so including a square like this one, you have two choices when you make that inversion. So remember the x squared looks like a bowl. And if you invert it, you're basically drawing a diagonal line and flipping it. So if you were to just invert it, it would just look like a sideways, kind of like a little bit like a pitchfork on its side. But that's not a function. So you have to choose: do I want the top side or the bottom side? And that's equivalent to saying when you take the square root of this, it's either going to be if I were to invert this to say, well, okay, if y is equal to x squared, what's x equal to? X is either equal to positive square root of y or negative square root of y. You have to choose based on your application. So if you're doing an inverse CDF to generate a random variable that is negative in that area, then you have to say, did I choose the right sign of this to make sure that random variable is negative? Or it might be just the way the forms, it might be you have to choose the positive version in order to make the whole random variable negative. But you have to sort of keep in mind, you have to just sort of keep in mind, like, what is my range that I'm shooting for? And if I have this in the CDF, which is a very reasonable thing to have in the CDF, or 1 minus x squared, that could be in the CDF, or x fourth. All of these things that are not invertible could be in your CDF. So when you take the inverse of them, you have to say, what's most consistent with my range? Is it this one or that one? So that's what question 2 is all about. So those are your tips for when you're doing that homework D2. And this will become more clear as we do more examples in class and once you've taken a look at the homework. The due date of this homework is lecture E2. So this Thursday is E1. So that will be, next week on Tuesday. So, and then that allows us to have this standard 4-day penalty-free grace period. And then the solution set will be released that. So what I mean by penalty-free here is because I've kind of compressed things on you, I am not going to have a late penalty on this. And so I'm going to make it due on this on Tuesday. But so that's technically when it's due, but I am going to suppress our 20% penalty for the rest of the week. So it's effectively due on whatever Saturday. So you can turn it in by Saturday. You won't get any late penalty. But it's technically due on, in order to be consistent with the syllabus, I would rather you have it turned in Tuesday night, but I'm not going to charge you anything because I've kind of compressed things to make sure that we get these two things in before the midterm. So if you need to turn it in Friday or Saturday, you're not going to get any penalty. It'll be as if you turned it in before the official due date. But Canvas is going to say that its due date is Tuesday, and normally that would mean 20% per day late for homeworks, but that won't be the case for this homework. So it's a special homework. The other thing that you're going to be asked to do realizations, don't submit just a sheet of thousands of realizations as your solution. That's not readable. No one, that doesn't show your understanding. The TA can't grade that, or the grader can't grade that. So show us histograms, plots, those sorts of things that are actually interpretable. You may have generated your realizations in a spreadsheet, and you might want to turn in the spreadsheet as a part of showing your work, but what should be in your main homework document is what we asked for, which is like a histogram of the realizations to sort of verify that it has the right shape and so on and so forth. And then, of course, in your plots, use descriptive titles, label your axes, do proper axis scaling. So like I said, mathematicians don't use units, engineers do. We label our plots because units really matter, so practice that. Okay. Otherwise, ICAF, this is another special assignment. It is due before lecture F, which is a week from today. That's our midterm review. It is a longer ICA than normal. And so you might say, well, I'll just take it as one of my drops. But it's a special one in that you can take it for as many times as you want, and you'll get the highest score from all of those times. It, you know, it is worth a lot more. So that means that if you don't take it as one of your drops, it'll buffer against ICAs that you didn't do as well. And because it's like taking 3 ICAs at once. And then it acts as midterm practice. So it effectively samples from all the other previous ICAs. So most of the, I mean, there's a couple of new questions thrown in there, but most of the questions, every time you take it, will be questions you've seen before if you've taken the other ICAs. So I encourage you to take this one. Of course, you can take it as one of your drops if you feel pretty confident, but you know, hopefully provided some incentive. And then, of course, the midterm, that's not next week, it's the week after that. There are a bunch of resources. I sent out an announcement. There's a little unit F1 before the unit F2 midterm, and it has just a lockdown browser compliance test. You basically go into it in lockdown browser. There's one question that you check a box and hit submit, and then you get a point for that. And that point actually counts as 0.5 or I think 0.25% of your final grade. Just automatically, you get sort of free credit for doing that. It actually takes that a little bit of credit away from the individual exam. So you just sort of, it's like you've already got 0.25 or some fraction of your individual exam done. And that just makes sure that everyone can take it with their laptop and then stage or with their computers, desktop or laptop. And then on stage one, which will be a week from Tuesday, then that will be the individual one, which you can come here during the class period to take if you want, but you don't have to. It'll be available all of Tuesday. And if it's helpful, I could even make it available, you know, Monday and Wednesday as well, if people think that that's a good thing to have a little bit even extra flexibility. But whenever it's available, I can't answer any questions about exam material for fear of accidentally giving away one of the answers. So I kind of have to become silent to student questions about course content whenever an exam availability window is open. So you'll basically anytime Tuesday, you can start the exam. You'll have 90 minutes. If you come to class, because there's a class that comes after this, it'll only be 75. But if you take it outside of class, wherever you'd like, you can have the full 90 minutes, and that extra 15 is just for technical issues, just getting things up and running or something crashes or whatever. There's a little extra buffer. I've designed the exam so that most people hopefully will, and this usually plays out about right, most people should finish it in an hour. Quite a few people will finish it in less than that, say 30 to 40 minutes, and there'll be a handful of people who take the whole time, and that's totally fine. But the goal was for the mean and median and mode to all be well under the 75 minutes. And so, but I still give you the 90. So you'll take that whole individual exam. You can, if you take that Canvas compliance test, you can go into the exam section right now after you take that, and there's like 4 practice exams from previous semesters, including one Canvas-based exam, and then the other are paper-based exams, and with solution sets. So you can review those. You can actually take the Canvas-based exam. There's a practice version there to try that out. That will be very similar to the exam that we'll have, like very similar format, similar types of questions over similar kind of content spread. So I definitely recommend you take a look at that before the exam. That's the individual portion. And then on Thursday, similar thing, but now it's open book, open notes, and you can collaborate with anybody else enrolled in the class. And again, I will be here during this time period. Both these cases, if nobody shows up, I'll probably leave after 15 minutes. But if you're here, I'm here. And then in this one, you can come here in class and you can talk with each other. You can work together. You can also do that outside of class. You've got the whole day to do it. You can use Discord. You can use Slack. The only constraint is you have to use your own notes, the book, Canvas, and people that are currently enrolled in this course this semester. But then otherwise, you're free to collaborate and use those notes, and it's the exact same exam stage 2 as stage 1. 80% of your score will be stage 1, 20% will be stage 2. All right, that was a mouthful. Are there any questions about that setup? Yep. Good question. Off the top of my head, I'm sorry, that's something I should know. But if you look at the tentative, if you go to the main Canvas page, it's like the 3rd link down. There's like tentative activity schedule. It's a PDF. You click on that, it will show how everything lines up. And then also, I think it's on the Canvas calendar. I'd like to say that You do have a lab, but you get 2 weeks to do it. I think that's how I set it up, but I'd have to go back and check. It's a little, okay, good, right. It's a little complicated because there's also the break coming up. And so, yeah. Okay, great. Any other questions? All right. And then, lab book is required from now on. We're using Arena. So we're going to be asking you to do exercise out of the book. So have access to the book. All right. Any other questions? Great. All right. So we've been talking about input modeling and trying to figure out how to select these probabilistic models. Last time we started going over the kind of standard models. These are the ones that are kind of in bold here that you will use as your initial building blocks as you start building more stochastic models up. As you get more experience, you'll use the kind of gray ones. All of the ones that I've listed, gray or not, are really common in practice. And then, of course, there are more. But like, if you happen to cover, like, have these down as your kind of probabilistic model vocabulary, you'll be in really good shape if you want to start building models. So these cover a lot of different types of inputs. But like I said, we only focus kind of on the bold ones. We went through the kind of exponential family last time. So we went through all the red ones last time, which are sort of the ones where people don't give me a lot of information. So, what's the best I can do? And then we went through the blue ones, which were all continuous and discrete based on the kind of the exponential, they're either built from an exponential or perturbations off of an exponential. So Erlong K, that's the sum of exponentials. Weibel is kind of a stretchy exponential. And Poisson is the count of events that are exponentially spaced in time. And so I just want to cover these green ones and then mention the Poisson process before we go into random number generation. So this is where we left off last time. So notice the slides changed here from this time to, so it's a little strange here. So this is a combination of the slides I posted for E1 today and D2 last time. So the Bernoulli trial is the where we kind of left off here. And this is a very simple coin toss. So Bernoulli trial is a random variate that has two states, let's say 0 and 1, -1 and 1, and one parameter, P, the probability of one of those states, where the other state is 1 minus P. And so the probability mass function is exactly what I just said. The cumulative distribution function just sort of builds that up, starts at 0, and then it jumps up and eventually to 1. So it goes up through this sort of step and then eventually up to 1. And you can think of it as a coin flip, a weighted coin flip, where if P is 0.5, it comes up heads or tails with equal probability. Simple thing, Bernoulli trial. Rarely will you use a single Bernoulli trial. Very often you use a vector of them, or you build them up into these other distributions like I'm about to mention here. So the more important one here, binomial distribution. These are all basically binomial and negative binomial are counts, different types of ways of counting things that happen when you have strings of coin flips. So a binomial distribution is a discrete random variable, so it's a count that is basically if you have n coin flips with success probability P, then you're counting the number of successes we would get. So I flip the coin 40 times. It's a fair coin. So then I get this discrete probability distribution or probability mass function that looks like this, which shows that on average I get 20 successes, but there are certainly plenty of times I get 8 and plenty of times I get 32. So that's the sort of fair coin. As you get more weighted, like this green one here, that's a 70% probability. And so this, I think, is a probability of failure. And so the 70% probability of failure here, and this is a count of successes, is saying that on average, I get, about 30% of the total number here. So this is n equals, oh, I'm sorry, that's why they changed it to n equals 20. So this is 70% of my 20 trials. So that's why the green one stops here. And 70% of 20 is about 14. So the average is 14, but I do sometimes get 20. and I do sometimes get 10. So that's what we're modeling with a binomial distribution. The cumulative distribution function here is S-shaped, and as we learned last time, inflection points and S-shaped curves are modes of distributions. So this has a little mode here, and that mode in the 20 corresponds to this inflection point in the S-shaped curve. So just a bunch of S-shaped curves that shift back and forth, binomial distribution. So this is, any questions about that? Just a count of successes. Just captures the variance, whereas normally we say like, well, if I have if you normally would say I've got a 50% chance of getting ahead in heads, and if I'm flipping a coin, then if I flip 20 coins, you'd say on average I get 10, but you almost never get 10 heads when you flip 20 fair coins. And this captures the variance then in what you actually get. Okay. And then this is, like I said, number of successes and fixed. And so then a modification of that then is the negative binomial. So this is a different way to count. And so rather than having a fixed number of trials and then asking how many successes or failures, however you phrase it, here we can say, how many trials do I need until I get a certain number of successes or failures? So discrete random variable, a count, is a distribution with R successes and a success probability of P. So it's the number of independent coin flips, that's what I mean by Bernoulli trials, until the Rth success. So this could be a very long amount. So basically saying I'm flipping this coin, how many coin flips do I have to get until I get 30 that come up heads? And that might mean 300, that might mean 3,000, that might mean 30. So that's what we're going for here. And the very special case, which comes up a lot, is R equals 1. How many coin flips until my first success? Or more often it's phrased, until my first failure. So if you have, every time I turn on that light switch, if there's a 5% probability that a light bulb is going to go out from the fatigue of being turned on, then I could turn that light switch on, off and on, and the sort of mean number of flips before failure would be kind of that probability times, like it'd be related to that probability. If I want that distribution of flips to say like, well, what is the spread of like how many times I need to flip that on until the light bulb goes out due to the fatigue of being turned on? Well, if it's 10% every time, then sometimes it'll be only 5 flips, sometimes it'll be 500 flips, and then there'll be a certain shape distribution. And that's what we get with the negative binomial. And so it's also, I'm surprised I didn't actually put I thought I had a plot of these. It's going to look similar to this, but you're not going to have a fixed range, because it could be very large. So depending on if this probability is very, very low, then I might need a lot of flips in order to get it. If this probability is very high, then I'm going to need at least R flips. So the minimum number of this is always going to be, R, but then if probability is low, the maximum number could be practically infinite. So it's a discrete random variable that does not have a finite range, but does have a minimum bound, which is set by R. So any questions on that, the negative binomial and the geometric? The geometric is sort of the discrete analog of the exponential. So the exponential is kind of like if failures are independent, how long do I have to wait in continuous time until the first failure? This is, if a similar idea, but instead of time smoothly going on, it's time clicking by. And I'm saying if there's so at the exponential, I'm saying there's a certain rate of failures. I get a failure on average every 10 minutes. Well, then how long do I have to wait for my first failure? That's the exponential. Sometimes it's 4 minutes, sometimes it's 4.5, sometimes it's pi minutes, sometimes it's 20 plus pi minutes. It's smooth. Here, if you discretize time, then you can say every time interval, there's a certain probability I'm going to get a failure. How many time intervals do I go by until that failure happens? And that's why we view the geometric distribution as the kind of discrete analog of the exponential. And that's why it also is memoryless, just like the exponential. So questions about any of that? So on an exam, you could imagine me asking, I have 4 light bulbs that could fail independently. Each one of them has a failure distribution that's exponential. What would be the best distribution I could pick for modeling that particular, sum of failure times or something like that? And then you'd have to say, well, okay, that's an Erlang 4, not a normal distribution, for example, even though a normal distribution is bell-shaped. And it's certainly not a negative binomial because I'm looking for continuous. So those are the types of things. Or I might say, here's a distribution that I described. What is sort of the situation that would best match how you might use this distribution to model? So those are the types of things I'm looking for. I'm not expecting you to memorize any of this. If you need any of this, I will give you it as a list of formulas at the top of your exam. So when you are making your formula sheets, you don't have to write any of this stuff down. If there's a special case to that, I will let you know before the exam. Yep. Oh, they're gonna be notes. I'm sorry. I hate calling them crib sheets or cheat sheets, but they're whatever, they're notes. You get a paid as hand produced notes. As long as they're not screen captures, they can be typed, they can be scribbled on a tablet, whatever you want. Mhm. Okay. And then the last really important one kind of pulls a lot of these things together. It's one that you'll see a lot in like 470 when you talk about queuing theory, and that's the Poisson process. So that introduces a new term. We talked about a random variable, so we need to also define a random process. A random process is an index family of random variables. What do I mean by that? Well, let me give a special example. A counting process is this family where it is a bunch of these random variables in that this t is sort of the time is up to this time. So what a counting process is like I could say from 0 to 5 minutes, how many events happened? Well, that would be in 5. From 0 to 5.5 minutes, that would be in 5.5. If I collect all of those together and say I want to model the random variables that are generated from all of those different times that I could ask you about, that's what's referred to as a counting process. So it is a collection of random variables indexed by another variable, in this case t, but it could be discrete. So it could just be 1, 2, 3, or whatever. This happens to be a continuous time. And a counting process happens to be one where the random variable that you're grouping together represents the count of things that have happened up until that time. So that's a counting process. Are there any questions on what I mean by that? About process versus variable? So a process is a collection of variables. Um, and then a special counting process is the Poisson counting process or the Poisson process. This gets confusing to students because we have a Poisson variable and a Poisson random variable is discrete. A lot of students at this stage will confuse an exponential random variable for a Poisson random variable because of the role of the exponential in the Poisson process. Don't fall into that. I don't want to call it a trap, but don't fall into that hole. Is that that a Poisson variable is discrete. A Poisson process uses both the Poisson variable and the exponential, but don't mix up the exponential and Poisson. So here's how a Poisson process is set up. There are no, it's modeling the count, it's modeling how individuals arrive. And so it's going to model counts, it's going to model rates, it's going to model sort of inter-arrival times and so on, all kind of together. So a Poisson counting process has no simultaneous arrivals. So in our system, we don't assume that any arrivals happen together. Or if they do, we model them separately as like in a batch process or something where we figure out how many arrive together separately. Is we're only focused on the individual arrivals. We say there's only one arrival at a time. Stationary increments. And so what we're saying here is that the distribution of arrivals between times t and s only depends on the distance between them. So we don't actually care about what time t is or s is, only the distance between them. So we're saying that larger intervals are going to collect more arrivals than smaller intervals. That's all it's saying here. It doesn't matter where the interval is, it just matters how big it is. And then independent increments the number of arrivals we get in one interval is independent of the number of arrivals we get in another interval. So if I know that I got 15 arrivals in this interval, and that's well above average, in the next interval, I can't use that to say whether that interval will also be above average. Every interval is independent of each other in terms of its variation from average. So once we have all of those things, we can equivalently say that, and this is sort of, you could view them as consequences of that, but you can also prove that if these things hold, all of those things hold too. So this is sort of equivalent things, but we'll just assume those are the cases, and then this follows. If that happens, and we're going to assign a mean intensity or a mean rate of arrivals to this Poisson process, then the distribution of arrivals up to any time is Poisson distributed. It is a Poisson random variable. It is discrete. It is a count of arrivals up to this time t, and that was going to be the length of the interval t times the intensity lambda. So if this is a Poisson process describing 5 arrivals per minute, and I'm interested in how many arrivals happen per hour, well, then I just multiply the 5 per minute times 60 minutes, and that gives me 300 per hour. And so then I go to the Poisson random variable with 300 as the parameter, and that gives me the distribution of arrivals in the hour. The count, it's discrete. Now, here's where it gets confusing. Not only do we have a Poisson discrete count, we have exponential inter-arrival times. So this is where it gets confusing, and where students often, when they hear Poisson process, they think exponential random variable. Or when they hear, which is actually okay to think because an exponential is in there, but when they hear Poisson variable, then they need to really be thinking discrete. Variable, Poisson variable is discrete. PVD, Poisson variable is discrete. And so for a Poisson process, the count is Poisson. That's where it gets the name. But the inter-arrival times between arrivals are exponential with that rate lambda. So this, I've been mentioning before, that the Poisson and the exponential are closely related, and that's made use of in the Poisson process. So if somebody says arrivals arrive according to a Poisson process with rate, 5 per minute, then that tells you that if you need to know the count in any interval, it'll be Poisson. But if you need to know the inter-arrival times between, it will be exponential, and you can go back between that. So oftentimes when you're taking data, like if you go to the airport, it's often easier to model, to count the number of people that arrive in intervals. But then once you go into arena, it's much easier to simulate the time in between those arrivals. And so you can then convert from one to the other because of this relationship. Okay, so any questions about that? About this relationship, Poisson process, Poisson variable, exponential random variable, and how they all relate to each other. This is the count up to any time, or the count in any interval. This is the spacing between any two arrivals. Okay. When you get more advanced, and we'll touch on this in lab 6 a little bit, because we'll talk about scheduling, is that there are Poisson processes in the real world where the rate changes over time. And you can imagine at an airport or at a restaurant, the morning traffic will be very different than the afternoon traffic will be very different than the evening traffic. And if you want to model that, you can't model the whole day as a Poisson process because that requires one rate. So they invented then the inhomogeneous or non-homogeneous Poisson process, which allows you to specify how the rate changes over time. And then there's ways to put that into sim tools so that if the rate is changing, it knows how to feather kind of those edges between rate changes. And in lab 6, when you learn about using schedules in Arena, you're effectively scheduling rates, exponential arrival rates, how they change. And Arena knows behind the scenes how to use this kind of fancy math to, if you've got like a really slow arrival rate followed by a really fast arrival rate, you don't want it to schedule an arrival that is so slow it's way in the middle of the fast arrival rate and then skip all those fast arrivals. And it knows how to deal with that. And that is why we just count on Arena to do that for us, rather than us having to implement our own inhomogeneous Poisson process. Okay. And then there are some nice properties of Poisson processes. I don't actually care that much that you know too much about these because these are more 470, but you can split Poisson processes, and you will often do this, and you'll see this happen in your sims. You'll have arrivals come in, and then you'll go into a decide block, and then some will go that way and some will go that way. If that decide block is just choosing randomly, the group that goes that way will be another Poisson process with a slower rate, and the group that goes that way will be another Poisson process with a slower rate. And those two rates will add to the rate that fed the whole thing. That's what we mean by splitting a Poisson process. And then likewise, you can pull them together. If you take those two and then bring them back in together so that they merge again, that will be a Poisson process with the original rate. And so that's like a cool property that allows you to build networks of these things, which is why they're so important for classes like 470. And that's why you'll see, like in 470, these queuing nodes, which are marked basically, they're saying here, this first one, the arrivals to this queuing node are distributed according to a Poisson process. And that's because of all the splitting and merging and stuff. That's one of the reasons why it shows up so much there. So, relatively few assumptions in the Poisson process. There are non-stationary ways to simulate them, and splitting and pooling allow for you to create these cool network models. And so if you're interested in reading more about that, I skip over chapter 6 in this class, so we focus more on the sim and less on the math. But this is also stuff, this kind of network queuing theory stuff is stuff that you see or introduced to more in classes like 470. So that's kind of the complementary material that will fill this gap in. All right, so any questions about that? That's the last basic input model that I need you to know. All right, so like in summary, I think I've got that list here. So if you need a cheat sheet to kind of go through here, I've created this kind of page that for each one of these distributions gives you a one-line explanation of why you might use it. It gives you the kind of notation we use, and you can see how many parameters it uses. So I go through each one of those. There's the other ones. I include some ones that I'm not asking you to know, but I just put them on there just for your information. Likewise with the discrete, the ones that I care about you knowing, and maybe a few that are just good to know in the future. So put that all together, and that's this here. So the ones that are in bold are the ones that I want you to start, consolidating in memory, so that when you see those types of processes, small p processes, you start knowing, okay, that is probably best modeled with this or this or this or that, so on and so forth. And that catches us up. So just one more time, any questions on any of these random variables, the random process? Okay. All right. Okay, so that brings us to the homework C2, and just in general, how do we start generating random things with computers and sims? So once we've selected a probability distribution, that's great on paper, but then how do we computationally sample from that distribution? How do we actually generate simulated arrivals that are, arrive according to a Poisson process? So, if I say that X is the lifetime of a device that inspects cracks and it's exponentially distributed, okay, fine. If that's a realistic input model, great. But then how do I generate that exponentially distributed failure time so that when I'm simulating these inspection processes on the computer, it actually generates failure times that sometimes are low, sometimes are high, but overall have the right distribution to them. And so this is sort of the density function that I would like to simulate. This is my exponential density that has got this mean. And so if I integrate under that, I get the cumulative distribution function. If I plot the purple area that I just integrated under, I get this right here. And as I've been hinting at, we can invert this CDF to be able to take uniform random numbers and generate exponential or any random variate we want. So I've got a bunch of uniform random numbers here. They generate numbers all across 0 to 1. There's no bias. Sometimes they're 0, close to 0. Sometimes they're close to 1. Sometimes they're in the middle. And they're just spread out uniformly. So the density function is flat from 0 to 1. But when I plot them through the CDF, through the inverse CDF, it spreads them out so that they clump down here and they spread out. So these become more rare, these become more common. And so what that turns into is the density function that I want right here. And so that's great. That's what we're going to be talking about in the next lecture, how to do this. And that's where you use a little bit of that calculus to do that. But how do you get this thing? How do you get the uniformly distributed random numbers? So I'm going to use that term random number. A random number is something that comes from the uniform from 0 to 1. A random variate is a random draw from any other distribution or any distribution generically. So a random number, that's a random number. So how do we get random numbers? All right, so von Neumann was one of the first to start experimenting with this because they were using stochastic processes and things like Monte Carlo runs, trials, when they were developing the atomic bomb, and they were trying to advancing this field, and it actually said, anyone who considers arithmetical methods, so the things that computers can do to generate random digits, is in a state of sin. So he was highly skeptical of the approach, but they had to kind of do that, which is kind of, I thought, ironic, because some of the earliest methods that we know about for people generating random numbers in a very programmatic way actually come from the work of a bunch of Franciscan friars. So it's kind of an interesting piece of history. So how do we get random numbers? Well, if you go to Amazon, you can actually buy books of random numbers. So if you open up those books, every page will have sheets and sheets of this. And this looks a little silly at first, but once upon a time when you didn't have access to a computer, and you just needed another 5-digit random number, it was actually common to consult texts like this, CRC texts of long chains of random numbers. You were setting up an experiment, you just flip to a page, you find it, and so on. Fortunately, we don't do that anymore. We have random numbers built into Excel, for example, the rand function, and some others. MATLAB, for example, has got a whole bunch of different ways to draw random numbers, but they definitely both do random numbers and different types of random variates pre-built. But are they reliable? Do we trust them? How are they generating them? So that's what we kind of know. And oftentimes you find that there are artifacts of the way of the random number generator that you've picked that show up in your simulation results. And you say, for this particular type of sim, I need a more robust random number generator that might take longer to generate its random numbers. And sometimes you have to go into the help files of these and say, tell MATLAB, don't use a Mersenne prime, use some other random number generator that is more robust, even though if I'm taking a million draws, it's going to take twice as long. So it really does come up. So how do we know that we've got a good random number generator? Well, these are two properties you should remember. These are two properties you'll definitely be tested on, and you will test for these properties in homeworks and things, and that's uniformity and independence. So we're going to go through what both of these are shortly, or basically briefly here. Uniformity means that they've got to spread out evenly between 0 and 1 with no bias. And independence means that when you draw one, you can't predict where the next one is going to come from, except for knowing that it's coming from 0 to 1. Those are our two big properties. So though I can formalize that by saying that each one of my random numbers is, comes from 0 to 1. So it has this probability density function. A way to test that is to say, if I divide my interval into smaller subintervals and then count how many of my produced random numbers fall into those subintervals, there should be approximately the total number of random numbers drawn divided by the total number of subintervals in each bin. And if I can meet that, and within some allowable tolerances, then I'm pretty happy that this is uniformly distributed. So, for example, here, let's assume there's an equal side to C. This is what I'm shooting for, an equal probability to see each of these 20 numbers. So a good set is if I roll this die a bunch of times, I might get this. And if I kind of look through here, I don't see any range of numbers showing up more frequently than any other range. So it's true that if I just bin these up, I'm not going to get exactly the same across every, say if I binned every number individually, I'm not going to get one of every number, or the same number of every number. If I create a bin of 2 or 3, I'm not going to get the same number in every bin, but they're roughly the same. So this looks pretty good. If instead I roll the die and I get this string down here, I see a bunch of repeats of 2, a bunch of repeats of 7. I never see numbers over 10. So that is non-uniform. So that we want a test for uniformity to reject this and fail to reject that. That's what we're shooting for. So questions about that, what I mean by uniformity. Does that make sense? Okay. The second property that we need is independence. And I already mentioned this basically means that for when I draw 2 random numbers, knowing one can't help me better predict the other one. So I know that they all come from 0 to 1. So knowing that they're from between 0 and 1, that's knowledge I already had. I can't increase my knowledge by knowing any of the other draws. And this is really hard in arithmetic, random number generators, because a simple random number generator might be just add 0.01 to the previous number. And that might give me uniform values, but I'll know that every time I draw 1, the next one will be 1.01 and then 1.02 and so on. So it'll be very predictable. So the probability of any future value is independent of any past value. And so, in other words, one die roll cannot be predicted by another die roll. This is a good example. This is a bad example. I took all these numbers and I just sorted them. So here, they're both uniform, but in this second one, I actually know that if I just add 1, and once I get up to 20, I go back to 1. Once I know the pattern, then once I draw 1, I know what all the rest of them are going to be. Whereas here, once I draw 1, I have no information about what the next one's going to be. That's what I mean by a violation of independence. So any test for independence should reject this and fail to reject that. So any questions about that property, independence, and how it differs from uniformity? Both of these are uniform. This is probably independent. This is definitely not. Okay. So we want to test for whenever we come up with a new random number generator, or whenever we're not sure the random number generator that MATLAB or Excel or whatever has given us, we need to test for these properties to see if they're adequately uniform and independent. So how do we do that? That's our kind of next part here. So if we want to think of how the first step here is to figure out how to generate, and then we figure out how to test. So how do we generate random numbers? Well, we could just throw dice, but that's not very practical to do if we're talking about a computer throwing dice, like a little robotic arm. We could draw from cards. We could draw a ball from a well-stirred urn. These are all things we could do if you're drawing one random number with a person. But how do we do that in a more automated way? Well, there are some people who do things like this, where they aim a camera at a lava lamp, which has got its little, it's got these interesting and unique patterns that are changing over time, and they take, all these patterns which might change in color and in shape, and they take that image and they take all those pixels, and they basically take all those pixels, which are just going to be a bunch of numbers, and they run them through a function which maps all of those pixels to a single number, and that's referred to as a hash. And these hashes, these hash functions, are designed so that if one pixel changes, it's very unlikely for the function to produce a number that's very close to the other numbers. So here you're using this physical process to drive this hash map. And there are websites that are out there that have cameras that are aimed at these things that are generating entropy this way. But that's not super practical. If you do need sort of like if you're designing an experiment and you do need a random number. Another kind of similar idea is sampling from atmospheric noise. Random.org does that. So they basically have weather sensors out there. They can draw, they can say what is a very precise reading of barometer in different places, add those things together, generate numbers that way, and that ends up giving you a pretty good and truly random number. But these two methods here are not really good for very high throughput. Like I need to draw a million random numbers and have my sim finished in 30 seconds. And going over the network and asking these people to draw random numbers for me isn't a great way to do that. So how do we do that in a more practical way that we can just implement on a simple computer? And so we want, the desired features. It should be fast. It should not repeat numbers until a very, very long cycle. So these aren't properties we test for. Like, so if I were to ask you, what are the two most important things about a random number generator? Don't tell me it should be fast and have a long cycle. That's an important feature of the method for sure. That's a desired feature. But the two most important features, if I ask that question, are uniformity and independence. Unequivocally, that's the top of the list. But then in order to try to get a uniform and independent, I need to design some method that I can run on that computer. And I want it, and this isn't, a good random number generator doesn't have to have this, but it's desired, highly desired, that the random numbers be generated quickly. And it's highly desired that I have to draw millions and millions and millions before the cycle repeats. The cycle will always repeat. You can mathematically prove that. There are a finite number of states that can be represented inside a computer. And because of that, it is impossible, because the computer doesn't have a true source of randomness, for it not to eventually repeat a cycle of numbers. But I want it to be very, very long until that happens. And then this is another kind of weird one, but given the same seed, so there's a way in which we can start a random number generator, I want the same sequence to come out. So this seems different than this one. Here I want a very long cycle. Here I want to be able to start a cycle over and over and over again, as I wish. And so the idea here is that I want this to be repeatable and portable. So the idea here is I run a sim and it has a really cool result. I then want to, but I didn't quite see why it happened. I didn't measure enough variables. I want to rewind the universe, and then before replaying my sim, measure a bunch of different things I didn't measure before. And then run that result again and see, oh, that's why the nuclear reactor melted down in my sim. It's because of this thing right here, this choke point or whatever that I wasn't paying attention to, but that's a really important thing that I need to know about. I then need to report that to my boss. My boss is a technical person, and he wants to, or she wants to investigate this herself as well. And so I then can tell her, here's my sim, here's the random number seed that I used. And so that's what I mean by portable. On my, Linux machine, and then I can then run the sim, but then I can give it to her on her Mac. She can run the same sim with the same seed, and she'll see exactly the same execution that I ran. So she can run the universe I created on her machine, even though it's a different machine. So that's what I want. So I want it to have a long cycle, but I want all of those cycles to be able to be indexed by this thing called a seed, so that every time I want an independent replication, I use a different seed. But if I want to rerun that replication, I use the same seed over and over and over again. And that's why you'll notice in Arena, every time you open Arena and run a model, if you close Arena and run that model again, and then reopen Arena and run the model, you'll get the exact same numbers out, even though it has variation, but it'll be the exact same variation. Because Arena, unless you tell it differently, will start with the same seed over and over and over again. Every time you run a new replication, it will move to a different seed, a different seed, a different seed. But every time you start Arena, replication one will always use the same seed. And that's on purpose. Okay. So those are my desired things. Any questions about these properties? They're not the required properties. These are just the desired properties. Required, uniformity, independence. Remember that. If you see that on a test, those are the ones we're looking for, not these. These are important. These are desired. But we rank the other two much higher than these. Okay. So in Excel, every time you open Excel, it generates a new seed by using the time. So every time you start Excel, if you have random down down your rows in one column here, it will then put into its random number generator a seed, which is basically the seconds since January 1st, 1970. It just dumps that in as its seed. So every time you reopen Excel, you have a different time, you get a different set of numbers. Unfortunately, in Excel, plain vanilla Excel, you don't have access to Excel's random number seed, so you can't control that. But with things like VBA, you can do that, but then you're not generating numbers the same way. Most good simulation programs give you access to the seed so you can rerun a sim over and over again. And that's why in Arena, there's a seeds element that we'll learn about later that allows you to actually put in a seed value so that if you've identified an interesting seed that has an interesting set of behaviors, you can then rerun your sim with exactly that seed and see exactly the same thing over and over and over again. So you can better investigate that apparently pathological but important case. Okay. Questions about desired properties? Seeds may not be that clear because we haven't used a seed yet. All right, so how do we build these PRNGs, pseudo-random number generators? So early attempts, these are not what is currently used. These are the Franciscan friars. These are the types of methods, though, that ended up leading to the methods we use today. And so there's like, can I come up with a recipe that is likely to get me the next number from the recipe, if I regenerate the recipe over and over again, will be likely to be very different than the previous number. And so this so-called middle square method, it would start with the seed was a 4-digit positive natural number, like 1, 2, 3, 4. It would then square that number to make it an 8-digit number that might have zeros on the front of it. And then it would set the next number to be the middle 4 digits of the squared number. And then that random number, so between 0 and 1, would just take those 4 digits and divide them by 10,000. And that would guarantee to get you a decimal between 0 and 1. And then you could repeat this process, just substituting your new number for your old number over and over and over again. Seems simple enough, seems like it might work, but it has problems. So if you start with, say, this seed here, then I'm just I square it, I get these 8 digits, I take those 4 digits, that's my number, divide by 10,000, that's my random number, take that, square it, do the same thing over and over again, and you can see here, it just sort of decays to 0. And once you're at 0, there's no getting out of 0. Square 0, the middle digits are 0, you're just stuck in zeros. The other problem you can get is cycles. So, and these cycles might be of length 1. So this is another type of fixed point here, like the 0. But here I started with 6,500, square it, the middle 4 digits are 2,500. But if I take that and square it, the middle 5 digits are still 2,500. So I keep getting 0.25 over and over and over again. That's not good. And then I can get more complicated cycles as well. I start with 2784, I do the same process, and it starts looking okay. I hit this, and these all look all right, but then I hit 5600 again, and then I get this cycle over and over again. And on top of that, it can be difficult to diagnose when this is going to happen. Because if I start with 9713 and do this, I do eventually get a 5 or a 4 number cycle over and over and over again. But it doesn't happen until value 84. So I go through 83 numbers that actually look pretty good. So, so this is not great, this middle square method. It's simple to implement. It has low storage requirements. It's pretty fast, but it's difficult to find good seeds. They tend to rapidly degenerate to 0 and have short cycles. So many other early pseudo-random number generators have exactly the same problem, and so we don't use them anymore. What is kind of the closest thing to a good random number generator that you actually see implemented now is what you manually implement on homework C2, which is the linear congruential generator. the LCG. And so the idea here is that I have these four parameters, a seed, as all good random number generators should have, and then a fixed parameter multiplier, a fixed parameter the increment, and a fixed parameter the modulus, which is the thing I'm going to take remainders from. And so the method is like start with my seed, and then as my first number, which will show up here in the formula, I multiply the seed or whatever my current number is by the multiplier. I add the increment, and then I take that number mod. So I divide that number by the modulus by this m value and take the remainder. And that will give me a number that's guaranteed to be less than the modulus. So to get my number between 0 and 1, I just divide whatever number comes out of there by the modulus, and that will give me a number between 0 and 1. If you change the parameters in particular ways, it comes with different names. So like if you set the increment always to 0, then it is, so that here would be always 0. Then that, or sorry, if always non-zero, then we call it the mix. If it's always 0, we call it the multiplicative because it just ends up being a times x mod m. But they're all just special versions of the LCG. So there's other names for it or whatever. It's there's this fancier one, the inversive one, where they basically add an inverted thing here. So it's just different ways to try to guarantee that we, don't get into cycles and so on. So there's a lot of different variations on it, but this is the core of it, and that's the one that you should know. You definitely know how to use an LCG. If I gave you a seed and I gave you these parameters, you should be able to calculate the next 5 numbers out of the LCG. All right, so what are the nice things about, what are the properties of the LCG? The maximum cycle length is the modulus. So if the modulus is small, the cycle length is small. So that it can be a downside because a lot of times we don't want these modulus to be, gigantic. But what's really cool here is that you can prove that if these properties hold, so if the only integer that divides the modulus and the increment evenly is 1, and that the multiplier minus 1 is divisible by all prime factors of the modulus. So another reason why it's nice to have a small modulus to be able to calculate all of those. And then if that multiplier minus 1 is divisible by 4, and if the modulus is divisible by 4, if all of those things hold, you can prove that your LCG will have a full period. And what that means is it will have a cycle of the full maximum period cycle. It'll have an m number cycle. So it's guaranteed that, it can't be larger than m, but it won't be any smaller than m. So that's great. We have guarantees on it. That's much better than the middle square method, which is one of the reasons why we use this. So here's our example. We start with a seed of 27. Here are the parameters. We plug in 27 times the multiplier. We add 43. That gives us a number that is 502. We then do 502 mod 100. What's the remainder when you divide 502 by 100? It's 2. Then you do 2 divided by this modulus, so our random number is 0.02. And so that's how we generate our first random number. So then our second random number is just going to take this 2 and repeat the process. And then we do that again for the third. I want to emphasize here, I'll get the question in just a second, that the first random number is not from the seed. So if I were to give you a seed and ask you to generate 3 random numbers, your first number should not be the seed divided by the modulus. Your first number you should go through all this, and it should be that divided by the modulus. Question? No, I just wanted you to show, I wanted to show that that this is so popular that there are other derivations that have come off of that. This is one that the book mentions. All I care about, this is one formula I won't give you, but you should know. So know all of this up here. Okay, so that's how we do that. Any questions on that? So here's an example. This has a modulus of 10,000 here. So these parameters weren't set up to have the full 10,000 cycle, but still, this is pretty good where I don't actually get a repeat until 2000. So just applying this over and over again, I get these numbers. But a real question is, how good of a random number generator is it? Well, if I take a histogram of those 2000 numbers, that is pretty darn uniform. So that's pretty cool. If I want to make the this have a longer period, then a trick that people do is a so-called combined LCG. And it's all the benefits of an LCG with a longer period. And all you do is basically create two LCGs and add them together. So that's, it's a slightly more complicated here, but it's basically you've got an LCG in your X variable, an LCG in your Y variable. Those two are going, doing their own thing. You add them together and take another modulus here, and that combined version will generate another random number that you can use, and it will have a cycle that is can be much longer than these two cycles. It's kind of like a beat, where like if this thing cycles every 3 and this thing cycles every 4, they don't ever actually meet up again until every 12. And so this can cycle every 12. It's kind of the idea here. And there are some great examples all the way back in 1986 where he created a combined LCG that had a huge modulus for that time. And now there's ones that are orders of magnitude bigger than that. So this is my simple example, which is not orders of magnitudes bigger than that. But I basically created an LCG here, that has a period of 4, an LCG here that has a period of 3. In this case, I subtracted them. I then took the modulus, mod 3. So I divided these by 3 and took the remainder. That gave me numbers between 0 and 3. So now, even though my modulus is just giving me numbers between 0 and 3, the period here is actually bigger than the modulus of the CLCG. So that's pretty cool because I can actually, like, even though I get this 1 is followed by 0, 1, this 1 is followed by 2, 0, this 1 is followed by 2, 1. So even though I'm getting the same number over and over again, I don't actually get the repeat cycle until well after it. Finally, this 1 is followed by 0 again. Question? It can be. So an example. So you can negate an LCG and it's still an LCG. So it's just kind of a linear or an additive combination of two LCGs is what the cumulative here is. And so, like, I'm using this example from the literature where he actually subtracted these two, and that it kind of, like how you find these really good combined ones is not trivial necessarily. And so, so this, like, once you have this, you save it, you encode that into MATLAB, and then in MATLAB, under the random number generator, there's a parameter where you can tell it to use that as its random number generator. And so exactly figuring out what form, modulus here, CLCs here, is kind of proprietary info, but the basic structure is addition or subtraction between two. All right. Any other questions on how those were generated? All right. So, like I said, there are now combined generators that have huge periods, orders of magnitude larger than that, and still ensure uniformity and independence. So that's the other thing. What I want you to, I want you to know how to use an LCG, a single LCG, and I want you to know why there are combined LCGs. And that reason is to take all the benefits of an LCG, but then give it a much, much longer period. Yep. Yeah, so it's over here in these columns. This one's got an interval of 4. So, and this one's got an interval of 3. If I, in this case, subtract them, 3 minus 2, I get the 1. I don't actually see 3 and 2 again until down here. So because this pairing doesn't show up until 12 later, this pattern doesn't repeat until 12 later. Yeah. So I'm finding, but basically all this combined thing does is takes a vector of CLCGs with different periods and then combines them into a scalar, which itself now will have a much longer period. All right. Great questions. Okay, so for closing out here, I want to give a preview of these tests then. And if we don't get through independence, then we'll cover this next time. But I think we can get through uniformity. So how do we test for uniformity and independence? Uniformity, we've already kind of described. We want to use a statistical test where we basically have a null hypothesis. A good result is that our random numbers are uniformly distributed. And so we want to see, can we reject that null? So if we assume that they are uniformly distributed and we look at the data, can we have a statistical test which says, no, that assumption must be way off? And if we can reject them, we know it's a bad number or bad random number generator. If we can't reject the null, that doesn't mean that it's a bad random number generator. It might just mean we haven't taken enough data. So that's something we always have to be careful of here. So we choose a level of significance. So this is how confident are we that, like how often do we reject our random number generator incorrectly? So usually we set that at 5%. And if you so hopefully from 380, remember, if I'm testing for how well do count data agree with distributions, there should be one place that your head goes. Does anybody know what statistical test we use to test whether counts are consistent with an expected distribution? It was murky for me when I was at your stage too. Whenever you hear count and statistical test, your head should go directly to chi-squared. That's what the chi-squared is for. A t-test for testing means, a chi-squared test is for testing counts. So this is the whole point of a chi-squared test, is to compare expected frequencies and observed frequencies. Our expected frequencies are if we have, I don't know, 1,000 draws and we've got however many bins I have here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 bins and let's say 2,000 draws, then I expect 200 in every bin. Well, I'm not going to get exactly 200 in every bin. The chi-squared will say, okay, your expected is 200, your observed is 205, is 196, et cetera, et cetera. It will then generate a test statistic, will say, how likely is the variable numbers that you got from a distribution whose expected counts is 200. That's what the chi-squared test does. So we're testing count data and frequency data. So what we're going to do is divide our interval by a certain number of intervals here. So this might be, 4 classes, 5 classes, or whatever. If the number of counts, the number of data we drew divided by the number of intervals is less than 5, you can't use the chi-squared. You have to use a Kolmogorov-Smirnov test. That's a different, which we will cover, but you cannot use a chi-squared. If your expected counts in any bin is less than 5, do not move forward with the chi-squared. That's wrong. Stop right there. There are ways that we can correct for this, but you can't move forward with a normal chi-squared. Count all of your observation in each bin, and then we'll go over this again next time. Calculate this statistic. Hopefully this will be review. Observe, that's how many I actually got in the bin minus my expected. So in my previous example, this will be 200 for every bin because it's a uniform. So I'm saying here, so for a uniform distribution, the expected number is this number for every single bin. And then I take the statistic that comes out of it and I look in my chi-squared table, and this is effectively a difference from the null. A large number here means it's very different from the null. A small number here means it's very close to the null. And so if your number coming out of here is greater than a threshold that you can look up in a table, then you reject it and say, that's a bad random number generator. Those are non-uniform numbers. And that's where we can pick up next time. So I'll do this example next time. So I want to give you an iClicker. And your iClicker to get out of here will be, give me one of the 2 most important things about a pseudo-random number generator. Give me one of the 2 most important properties that every pseudo-random number generator should have. There are two properties that should be burned into your brain. Give me one of them. And that's all I've got for you. So we'll see you Tuesday to finish this up and then do some random variant generation.